Alright, so we're going to do number 4, and as you can hear, my voice is not strong today, so make sure you can't hear me, just move a little closer or something. Alright, so you've got these two forces, these two boxes, pushing on them. So do we have friction? Frictionless floor, so no friction. And we're pushing on. So since we're pushing them and we don't have friction, does it make sense that the boxes are going to be accelerating? Yeah. So, okay, so we're going to start off by doing our force diagrams. So this is number 4. And we first need to do one of the system. Make sure bigger. So my system looks like that. And then I need to do one of the large box. And maybe I can put these things over so that I can fit it all in. Okay. And one of the small box. So I need 3 force diagrams here in my Y. It's up to you on your system whether we know that each box has its own weight. I like to combine them into one weight, just like I like to combine the inertias. So it tells me the mass of box A is 12.7 kilograms and B is 7 kilograms. And I am actually going to write those right on my diagram. You don't have to, but it's not a bad idea to keep track of them. That means the mass of my system is 19.7 kilograms. My system is going to have a weight, F sub G, and we'll call that total. It's going to have a normal force, total, and we're applying a force to it. I think they tell me how big that force is. For me, it's 7.5 newtons. So I could even just put that right in, 7.5 newtons. So over here, box A has a weight, so F sub G of A. It has a normal force of A. It's being pushed with a force of 7.5 newtons. It's pushing on the smaller box, so that means the smaller box is pushing back on it. We'll call that force F. Smaller box is being pushed by the larger box, so that's going to be that equal and opposite by Newton's third law. Just like a tension, except a push rather than a pull. We'd have the weight of B here. We'd have the normal force of B. And then all I need to do is indicate that all of these are accelerating to the right with the same acceleration. That's what makes them a system, is that they're all accelerating, moving together. If they're moving separately, the math gets a lot more complicated, but fun. All right, so those would be the 3 force diagrams you would need for full credit on Monday. This was the problem. All right. And now I'm only going to use the free bodies that I need. Let's see. They asked me, I think, to solve for the acceleration, the force between the boxes, and then if this Alex was to push from the other side, how would the answer in B change? We'll do that. Would actually be a different set of force diagrams, but we'll do that on the lower part. All right. So acceleration. I'm going to use the system for my acceleration. I'm actually going to start here so that I use as little space as I need to. So for the system, remember I start with my equation. Sum of the forces equals ma. And I want to first express that equation graphically. I do that by doing the free body diagram. So 19.7 kilograms. There's a force up. It's the force 7.5 newtons to the right. Force down. And there's an acceleration. So now I've taken that equation and drawn a picture of the equation. Now I might as well write it in math terms, right? Do I care about, I want to separate it into x and y just to make my math easier. Which one do I care about to find the acceleration? The x or the y? The x. Now, is there any friction? No. So I really probably don't have to worry about the y. Remember, friction takes into account the normal force, so a lot of times there's a crossover. But here I probably just need to worry about this equation in the x direction. So let's do that. Let's see. Sum of my forces, total force in the x is 7.5 newtons. My inertia is 19.7 kilograms. And my acceleration, I don't know. But I can find my acceleration. So, calculator time. 19.7 divided by 7.5. Nope. Messed that up. 7.5 divided by 19.7. 0.381. So I get 0.381 meters per second squared for the acceleration of the system. Good on that or a question? All right. So now it asks me to find out this force in between the two boxes. I could actually use either force diagram. I could use either the small box or the large box. I'm going to pick the small box because there's less forces on it, so probably less math to do. So I'm going to, again, start with my same equation. Sum of the forces equals MA. And draw my picture of that equation. And I have a force F. I have a normal force of A, the weight of B. And I know it's accelerating at 0.381 meters per second squared in that direction. So again, I'm only going to worry about the x direction in this example, this problem. And now take that picture and write it mathematically. I get F equals, oops, I forgot to write my inertia next to it. My inertia is 7 kilograms. Equals 7 kilograms times 0.381 meters per second squared. And so I get F equals, now in my writing it down I rounded, but luckily I have the answer to the previous in my calculator, so I don't have to round. And I get 2.66. How about that? The second part. Good? All right, so the third part of this one says to us, what if they were pushing on the other side of the box, and that changes our force diagrams. And what that changes in our force diagrams over here, maybe I'll do them in red. Still have the 12.7 kilograms here. Still have an F here. Still have the same acceleration. It doesn't change the acceleration because what it does on the system, it changes the direction of the net force to change the direction of the acceleration, but not the magnitude of it. Doesn't affect the weight or the normal force. But does affect F. Because I'm just going to find these out real quick. It does affect F because now 7.5 newtons is pushing on the smaller crate, which is pushing on the larger crate. And if you look at the difference in the force diagrams, you can see that if there's going to be a difference. So let's use this one, the 12.7 kilogram box. I'm going to use that one again because it just has less forces on it. Although I could use the 7 kilogram one. The way I tend to look at it is I look at the top one here, the one that's in blue and black, and say, oh, F, the force, is what's creating the acceleration of the 7 kilograms. So it's going to be a certain size. You know. Now F is the only force that's creating the acceleration of the 12.7 kilograms. So it's going to have, if it's creating the same acceleration, it's going to have to be a larger force because it's causing the same acceleration but in a greater amount of inertia. So it's going to create a larger force. So if I get an answer for this last part that's not bigger than my answer for part B, I'm going to double check before I even enter an answer because I'm expecting a larger answer. So I'm going to do this using this red diagram of the 12.7 kilogram block. So I'm going to go down here, and I'm expecting an answer bigger than 2.66. So let's see what we get. Again, doing that equation graphically of the 12.7 kilograms. 12.7. I have F, FGA, FNA, same acceleration. So my acceleration is still 0.381. On the system, all that happened was we changed direction. We didn't change the inertia, we didn't change anything else. Now that I've written the equation as a picture, now let's write it in math terms. You guys okay if I take to the left to be positive? Since everything points to the left, that way I don't have to deal with negative signs. I know some of you that will bug, but you'll get over it. Inertia is 12.7 kilograms. The acceleration is 0.381 meters per second. So my force, I want to do 12.7 times 4 4.84. Oh, good. So it's larger than my 2.66. That makes me feel good that I got it correct. Pause. All right, so we're going to go on to number 5 here. In 5, we've got the two blocks sitting on top of each other, and they're pulled with a constant velocity. Ooh, so if they're pulled with a constant velocity, do you think there is or is not friction? Okay. Now, what does it mean to be at a constant velocity? Why'd you change your answer? Right, because it has to have a zero acceleration. If it's got a zero acceleration, what's the net force on it? Zero. Net. Remember, that's what our equation says. Sum of the forces, but net force, the total force, causes acceleration. That's what's going on here. So, all right. So we need to do 3 free body diagrams. 3 force diagrams here. Yeah, I know in C and D it changes some of the parameters, but you wouldn't need to do new force diagrams. So we need to do one of the system, one of the lower block, and one of the upper block. And let's see what else they tell us. They tell us in the first case, the inertia of this is 2m, and then this is m, and this is m. And they just call that force F, okay? So, there's a force F applied here. We would have a weight, so let's call that the weight of the system. We'd have a normal force of the system, and we'd have a frictional force of the system back that way. No acceleration, right? So here on the bottom one, which one was labeled number 1? Let's see. Bottom one's number 1. Okay. So on number 1, you would of course have a weight of 1, and it would have a normal force on number 1. It's going to have a force pulling it in that direction, and it's going to have this frictional force on it also. Then I look at the top one and say, oh, okay, it's going to have a weight down. But wait a minute, if it's pushing down on the bottom block, then I must add in a force here of it pushing down on the bottom one. All right? I mean, think about holding something in your hand. Don't you feel the weight of that object pushing down on your hand? So the block is going to feel that weight. If it pushes down on the bottom one pushes up on it. Now, since it's not accelerating horizontally, is there a frictional force? Do you think there's a frictional force on it? Or ask yourself this, if I leave it like this, would it have a zero acceleration horizontally? Vertically, would it, well, let's do horizontal and then we can talk vertically. But horizontally, would it have a zero acceleration? Yes. Could it still be moving, though? Yes, because it has inertia. So no net force means its motion's not changing. And then vertically, it could have with no acceleration because those two could balance out. In fact, those two would have to balance out, right? Here? No, because this one, and I'm going to draw my FN1 in a different place just to clarify. I'm going to move this one over. And this FN1, we could actually probably more accurately draw there. Because it is actually, and so we could actually move this one here. So that's the force of the surface pushing back up on it. I can see, yeah, definitely that's a better place in this diagram to have this. So I think we're complete there in our force diagrams. All right. So they want to know the normal force exerted by the surface on the bottom block. So they want to know, so I would say let's do let's use the force diagram of just the bottom block. And of course, start with our equation, right? Sum of the forces equals ma, since that's our only equation. Always a good one to start with. Input to that equation by drawing. M. Let's see. FN1. FG2. FG1. F. And frictional force. So there's writing my equation in a picture. I'm interested in F normal 1, so I'm going to just try dealing with the y direction, see if I can find it, and then move on from there. So now, mathematically, I'm just going to write that equation again, but only worry about the y direction. So this would be in the y direction here. I would have Fn1 minus Fg2 minus Fg1 equals m for my inertia times my acceleration of 0. And I think the only other factor I need to remember is look up on my equation sheet to remember that the weight of something is its mass times the gravitational field strength little g. And then just substitute in and you should get your answer. Right? A little algebraic rearrangement. Then looking at part B, the normal force exerted by the bottom block on M2 on this top block. So I'm going to use the top block's free body for that, or force diagram for that. And so I would start with my equation. Sum of the forces equals ma. Draw my free body. The weight of block 2. The normal force on block 2. It has an inertia of m. Now that I've filled in my equation graphically, filled in using math, write it in math again. And then just rearrange substitute.